Okay, so thank you very much. Thank you for having me here today to discuss this phase transition that we've identified, I suppose, in lattices of non-equilibrium condensates. So to launch right into this, I suppose I don't need to really introduce polariton condensates. We've heard lots of the wonderful things that can be done with them over the last number of days here. So in particular, yeah, we're associated with, we're interested in the interesting phenomena that are associated with the non-equilibrium nature of these condensates. And in particular, we're interested in the impact that disorder can play, because previous works have suggested that, in fact, a disordered potential landscape can sometimes destroy the long-range phase order that is the signature of condensation. So in order to probe this, we consider some chains and lattices of spatially separated condensates. And in a similar way to this, this paper from a couple of years ago by Hamid Ohadi, yeah, they kind of did an experimental look at these lattices. But anyway, yeah, we're interested in particular in the conditions that allow these condensates with initially randomly detuned energies, how they can synchronize their energies and their emission frequencies. So, of course, the synchronization of energies could then allow the establishment of a single condensate across the entire system. So, our starting point, as is so often the case, is this driven distributive Gross-Pitievsky equation here. I'm sure you've seen it a few times at this stage, but just to quickly run through it again, we have a nonlinear Schrodinger equation where we consider polariton-polariton interactions, and then we model a non-resonant pumping through these gain and loss terms, where G is just the net gain of the condensate as a result of scattering into the condensate from the reservoir, and of course it includes losses from due to the finite lifetime of the polariton as well. And gamma is our second order gain term, and that, I suppose, models how, as the condensate gets built up, it depletes the reservoir, which slows its rate of its gain rate. So to consider a chain or a lattice, we'd expand this over the wave functions of each site. And this gives us a number of coupled equations. So we consider randomly distributed on-site energies, which we call epsilon here. Generally, we consider in this work Gaussian distributions, but that's not really important to the results. And the standard deviation of these energies, I suppose, is how we kind of track our disorder strength. Then we assume that each site sees the same interaction strength and the same pumping, just for simplicity, I suppose. And then the final term here, this J, is our Josephson coupling, which describes how condensates can tunnel through the potential barriers to their nearest neighbors. And this, of course, is the mechanism that enables synchronization to take place in lattices of condensates. So, yeah, the previous formulation wasn't the most intuitive for understanding how synchronization might work. So we substitute in the explicit form of the macroscopic wave function to allow us to write a couple of equations in terms of both densities and phases of each site. And by doing a bit of work with this, we were able to adiabatically eliminate the density at each site, and this gives us this nice phase equation here, which we use to describe the system. So you can see we have an equation in terms of a phase at each site. And again, we have the onsite. This shows the onsite energies are blue shifted by interactions. And then this sum here is over nearest neighbors. And it shows that each site is coupled to its neighboring sites through these trigonometric functions of sine and cosine. So yeah, basically this model that we have written down here now it's basically a model for a couple of nonlinear oscillators. We might not necessarily be talking about polaritons anymore. It's a bit general. So what we're interested again is it's in the synchronization of the frequencies of these nonlinear oscillators. Yeah, I've got a bit of just to clarify what we mean by this, we've got a little animation here which shows that these first three rings, balls on a ring even, have the first three show frequency and phase synchronization. So that's their frequencies are synchronized. So we're happy with that. The second one, even though they're out of phase, they have frequency synchronization. And that's also sufficient for what we're looking for. And then our third set, we just show these start off at the same phase, but their frequencies are not synchronized. So they quickly lose that phase ordering, and that's not frequency synchronized. So yeah, just so we know we're all on the same page when it comes to synchronization. Okay, anyway, we're not the first people to study synchronization at all. It's it's been a hot topic in many fields for decades. And the most, I suppose, one of the most successful models, and simplest as well, that describes coupled oscillators is this Kuramoto model here. And we've written down the Kuramoto model with nearest neighbor coupling. It's just, again, it's a phase-only model, which has a sinusoidal coupling term. And these are the initial natural frequencies. So a lot is known about the Kuramoto model. In particular, it doesn't support synchronization in the thermodynamic limit. So as we go to infinite system sizes, it can't sustain a single frequency across the system. And there's a result for 1D chains, which actually it's known that for a finite chain of length n, the coupling strength k must be of order the square root of the chain length. So yeah, just to remind you what our model is, it looks quite a bit like the Kuramoto model. In fact, the only real difference is this cosine term here, which it turns out is actually quite important because it means we don't have an odd coupling term. Sine is an odd function. The cosine just makes it non-odd. And then the ratio of our two nonlinear terms are our interaction strength and our nonlinear gain are what set whether the sine or cosine kind of dominates this coupling. And yeah, as I said, it looks a bit like the Kuramoto model, and we see it can behave like the Kuramoto model as well, because what I've plotted here now on the right is the probability of synchronization for chains of varying lengths. Now we've made this fraction, this u over gamma, made it very big to 100. So yeah, so what we see is that so yes, to get these probabilities of synchronization, we solve our system for 100 different disorder realizations for each value of the coupling strength or the tunneling strength, and we see that in each case we go from a desynchronized state where there's not a common frequency across the chain. But as we increase our tunneling strength, we end up with a synchronized state eventually. However, this occurs at greater values of tunneling as we go to longer chains. So in fact, we can try this to scale, see if the Kuramoto scaling is what we're seeing, and it's exactly that, because when we scale by root n, all of our probabilities fall on top of each other. So yeah, it looks a bit like the Kuramoto model, but of course, if that was the case, then I wouldn't really be giving this whole talk here. So yes, more generally, that's not the case. So this plot here, it looks quite like the one I just showed you, but the crucial difference is we haven't scaled our x-axis at all. This is just the probability of synchronization as a function of the tunneling strength. And again, we go from our desynchronized state for low tunneling strengths, and as we increase it, we see the transition to a synchronized state. And this transition always happens at roughly the same tunneling strength. It's not, we don't see any scaling with system size. So yeah, this is interesting for a number of reasons. I mean, mainly because, well, first of all, it's distinct from the Kuramoto behavior, and also it looks quite like a phase transition. We see the transition from desynchronization, to synchronization as a function of the tunneling strength. So the next question, I suppose, is how do we describe this? And yeah, we can do some maths. The way we proceed is to expand the sine and cosine terms in our phase equation. Now, obviously, this requires small phase differences between neighboring sites, but we were justified in doing this because, well, first of all, so this will always describe if there's a small phase difference. This requires that the chain is synchronized or that the lattice is synchronized, because if we have different frequencies between two sites, the phases will be driven apart, and they won't confirm. This approximation won't work, I suppose. So this is for a synchronized system. So once we expand these trigonometric terms, we can linearize trigonometric terms. We can map this to a continuum model rather than a lattice model, and we end up with something that looks quite like the Kardar-Parisi-Zhang equation here. So yeah, the connection between driven dissipative Gross-Pitievsky physics and Kardar-Parisi-Zhang physics has been shown before by a number of different groups, I think. But this is the crucial difference in this case, in that we only consider spatial disorder. So our noise term here, our disorder term, does not depend on time. So this actually puts us in a different universality class to the traditional Kardar-Parisi-Zhang equation, which it was actually originally used to describe stochastic deposition and interface growth, and that tends to have a dependence on time in the noise. So there's a little bit more work to do to extract the scaling behavior that we're looking for. So the way to go about this is to perform this Cole-Hotz transformation, which allows us to write our Kardar-Parisi-Zhang equation in a slightly different form. And as I've written up here, but you might recognize this. This looks quite. This is just an imaginary time Schrodinger equation for a particle in a random potential, because again our epsilon here is random. And I've written, we use Z for the wave function, partly because to avoid confusion with the condensate wave function, but also because this model was used before to describe the partition function of directed polymers in random materials. But that's kind of another story. So anyway, we know what the solutions of the Schrodinger equation look like. They look a bit like this. And then, of course, since we had imaginary time in that equation, they're all going to decay. Furthermore, for random potential, we know that the low-lying states are going to be localized in the dimensions that we're interested in anyway, in 1 and 2 dimensions. So yes, the answer will look a bit like this. And we can check this theory by looking at some phase profiles. So here I've plotted the phases of a 1D chain of 800 oscillators, or 800 condensates. So this is the phase as a function of sight. And we see at small times, there's a number of different kind of peaks in our phase profile, which corresponds to a number of localized states. And then as we go to longer and longer times, these peaks, the higher energy peaks terms die away, and eventually we're left with just the ground state peak here. And then below these, I've plotted the frequencies that correspond to these phases. And so again, you see at small times, a number of different frequencies are present. We've got lots of different kind of flat levels here, a number of different energies as well. Frequencies are the same as energy, of course. And then as we go to longer times, we see the synchronization happening as the frequencies kind of spread out across the chain. And finally, we end up with the synchronized state. So the same behavior, the same phase behavior is indeed evident in 2 dimensions. This animation here just shows how the phase evolves in time on a 2-dimensional lattice. So, okay, so what we really want to know is what the phase boundary between the synchronized and desynchronized states look like. And we can find this by doing just a bit of a self-consistency check. So we're still on a lattice, and all our current terms, our phase gradient terms, came from the sine and cosine term in our original model. So the compactness of the trigonometric terms mean these are bounded to be less than or equal to 1. So that's a condition that this theory must fulfill. We can also calculate how the localization length looks like. For our model, it looks a bit like this. And then if we sub that into our value for the gradients of the phases, we have this condition which says that for a synchronized state, the tunneling strength must be at least of order the disorder strength by this power of the ratio of nonlinear terms. So yeah, that's we can check this with some numerical simulations more. So on the next slide here, I've plotted 2 phase diagrams for our system. So on the left we have a 1D phase diagram, on the right we have a 2-dimensional one. And as I said, the critical tunneling strength at which we cross over from desynchronization to synchronization, it goes with gamma over u, the square root of it in 1D, and it goes linearly in 2 dimensions. So on this log plot, you can see I've got we've plotted gamma over u with a slope for half. And the points are critical couplings, which we calculated by whenever we found out when the probability of synchronization was a half for a particular j. That's when we decided that j was critical. And we see it fits quite nicely to this line in 1 dimension. Now, as we go to larger gamma over u, it does start to fall off, but this is due to finite size effects. And I mentioned these earlier, where at small system sizes and at larger gamma over u, or u over gamma, it starts to behave a little bit like the Kerr-Motor model. But this is so I plotted the Kerr-Motor scaling here as well. The Kerr-Motor model goes differently with gamma over u. But in general, when we're not seeing these finite size effects, this agrees pretty well with our theory. And then in 2 dimensions, again, it's now a linear relationship between the tunneling and the nonlinear ratio. And yeah, we can see the clear distinction between our desynchronized phase down here and our synchronized one above. So that's kind of all I'm going to talk about today. We can draw some conclusions from this. So we did develop this theory where we wrote the dynamics of the carbon condensates in terms of their phases. And of course, this gave us this transition from desynchronized to a synchronized state, which crucially did not depend on system size. It seems to be there if we go to large systems and long times. From this, we were able to build a theory to extract this scaling of the critical coupling strengths. And yeah, I suppose this isn't just relevant to polariton condensates. Our phase model is potentially, I suppose, can model other systems of oscillators. And as far as we know, no one has shown this phase condition for this particular system of oscillators. So that was new. And then just some potential future work is that we might consider adding a time dependence to our noise, which will give us probably a slightly different universality class at the end of the day, but that's the future work. So thank you very much for listening, and take any questions.
Well, thank you for this very interesting talk. Well, yes, the work is now open for questions. Please raise your hand. It's time to wake up and yeah, ask. We have now time for some reasonable questions. We are not behind the schedule. Well, let's start with my questions then. I have two of them. So the first one will be, well, in your model, in the initial one, which is the Schrödinger equation with pump decay and things like that, there is no energy relaxation. And what do you think could be the consequences if on the behavior of the whole system, if it's on the slide 3? Yes. Yeah, here.
Sorry, we're talking about this model here, yes?
Yeah. Well, here there is no energy relaxation. If you, for example, put particles at some frequency, they will stay at this frequency. They can decay, but they cannot change the frequency.
Oh, yes.
Well, whereas there are ways to include, for example, decay which depends on kinetic energy. Then high energy particles will decay faster, and it will lead to overall. So what do you think could be the consequences on the behavior concerning this synchronization story? It might favor synchronization, for example.
Yes, yeah. I don't believe it would inhibit it, and I don't think it would have a kind of qualitative difference in what we see. But to be honest, I'm not entirely sure right now. I'd have to think about that one.
Well, at least it might be reasonable from the point of view of description of polariton condensates or polariton clouds, because for them there is definitely some energy relaxation with phonons, with other excitants. If you imagine that you have a non-resonant reservoir, then there is an efficient energy relaxation using these excitants in the reservoir. So,
yes, of course.
A second question is that, well, let's first ask if there are some other raised hands. Anybody else wants to ask a question? No, not so far. Well, so the second question is that, to summarize, you start from the Schrödinger equation, then you have some Kuramoto-like equation for the phase, then you have some KPZ equation for the phase, and then you come back to the Schrödinger equation in imaginary time. And this final Schrödinger equation in imaginary time, do you solve it numerically for the pictures that you have shown? And if yes, then is there any advantage over solving numerically directly the initial Schrödinger equation, where we are supposed to have less approximations? By the way,
no, so sorry, go on.
No, please.
Yeah, so actually we don't. So it's this slide where we have the
this slide. Is it solved numerically or analytically?
We solve their numerical results, but they're not for the Schrödinger equation in imaginary time. They're for our phase model from a few slides ago. So they're for this set of equations. So we can get this. We just solve these for the phase and the frequency. That's quite easy to do. And then we just show that the behavior.
So the pictures on this slide are not do not correspond to what is written in the upper part, which is the solution of the Schrödinger equation. The pictures here come from the equation for the phase.
Yes, but we've shown the equivalence between these two equations. So we started with all the simulations are from our phase model that we got from the Gross-Bit-driven bit of Gross-Bit-Yevsky equation. And then we just show here, sorry, on the previous slide, we argue that this is equivalent. Yeah, I suppose when you go from a lattice to a continuum model, this is the continuum version.
Okay, just to be sure, these power laws that you find on the next slide, they come from they come from the equation for the phase.
So the power laws were derived using the continuum equation. So the KPZ and But then we test that against simulations of our phase equation of the original one, and they agree with them. So
Schrödinger is imaginary time Schrödinger is ultimately not used. It's just written for general culture.
It's just a way of understanding the. We use it to understand the KPZ equation. It's just the KPZ equation written in a different way.
Okay, but still you work
with maybe that wasn't
KPZ
clear.
Directly.
Yeah, it's the KPZ, but it's just that's the KPZ with its transformation.
Okay, looks like I have made well. It's because of me that now we are again behind the schedule. So thank you very much.